University of Iceland Research Center in Husavik. So to add some introduction, the harbor porpoise is a species that is widely distributed, but is reproductively isolated. So we find two different species, the Phocoena in the Atlantic Ocean and Phocoena Marina in the Pacific Ocean. These species, due to their small size, they have to stay close to their prey and they have to avoid long periods of fasting. And they normally prey on herring, capelin, and sprat, but they are also hunted by dolphins, sharks, and killer whales, so avoidance of areas shared with this species has been suggested in previous publications. This is going, okay. Iceland is located in between two ridges, so it has very interesting oceanographic characteristics, and it has very unique flow dynamics. Due to this, the biological cycles are determined by these currents and determines the distribution of cetaceans as well. The environmental variables that we are going to assess in this project are going to be the slope that relates to the shape of the seabed and its structure with the distribution of cetaceans, also the depth, because it gives a differential distribution of prey, the aspect, that is basically the direction that the slope faces, the distance to the coast, because it's been seen important as determining breeding and feeding grounds, the location in the bay, to compare with also other analyses like the kernel densities and the sea surface temperature, that is a dynamic variable that determines distribution of cetaceans worldwide. Because this is done in whale watching boats, I just want to give an insight on this. It has many positive impacts because it creates great socio-economic development. It's actually one of the main industries in Iceland, but it also has some negative impacts in the cetaceans, and there is this code of conduct that is a basic guideline on how to approach the cetaceans, but it's not always followed, as we experience. The objective of this project, therefore, is assess the annual and seasonal trends in distribution using kernel density maps, analyze harbor porpoise sighting effort, analyze also differences between years and between months in the SPU values. I also wanted to check the sea state influence in the sighting ratio for porpoises and correlate through GAMS analysis the environmentals and the sighting of the porpoises. For the mathematical methods, first of all, we want to find the bay. It's Skjálfandi Bay, even if everything is out of place. It's approximately 25 kilometers long, and it has 150 meters of average depth. And it's a very interesting bay, as we saw before, because it has two major streams. This has the influx of these two rivers. One is coming from the permanent glacier in Iceland, and the other one is coming from a lake close to this area that is a volcanic lake, and this gives an input of fresh water that lowers the salinity and increases the nutrient concentration in the bay. We also have the town of Husavik, that is a fishing town as well as whale watching. The data collection was carried on traditional wooden vessels from the whale watching companies in sea state maximum 6, more or less, and the speed of the boat normally was 7 knots. Data was collected by 2 researchers normally with a camera for photo ID purposes, and this was put in the Spotter Pro, that is the software that we use with the iPad, in which we put the environmental, the sightings, and we also got the track lines from the boats. Data collected was quite messy, so I had to create a standardized protocol with my colleague Chloe Senglad here today, and we applied some filters and deleted the data with poor survey conditions. We recalculated the coordinates by bearing a distance from the boat. We also recalculate location by effort. We standardize every trip per 3 hours, and sightings that were very close in time, less than 15 minutes, were redundant, so we also delete them, and we got the final data to work with. For the data analysis, we first calculate the SPU. The SPU is the sighting per unit effort, and this is basically the number of sightings per the effort spent looking for whales. This gave us a total amount of 10,182 tours, and porpoises were recorded in 80% of them. Years and month differences were assessed by critical whales test, and in between years and in between months, we check for differences with the will constants. For the sea state, we simply ran a binomial GLM to check how this was affecting the sighting rate of the porpoises. We also did some kernel densities, which are basically non-parametric spatial statistics in which we define home range boundaries. This assumes that the data is independent and identically distributed, and the resolution for this kernel was 50 meters due to the data the set that I had. This was carried in RStudio using the KD2D function, the mass package, and the LSTV method, and is standardized for this kind of ecological studies. I also did this GAM analysis that is basically a non-parametric extension of a GLM, so it gets the linear function and it makes smooth terms. This is a very robust approach for cetacean habitat modeling, and for this I had to extract the environmental data from the bathymetry layer by using the terrain tool in QGIS, and we also calculate the distance to the coast with this software. The sea surface temperature was taken from Earth data NASA in a monthly basis. To put all this data together, well, here I should have some maps that we did. And to put all this data together, we created a 0.4 kilometer grid in which we calculated the average of all these variables, and the response variable was calculated by a TER index, that is a percentage of positive surveys in which porpoises were seen, weighted by the number of porpoises seen. And for the explanatory variable, we also did something similar. We transformed this because they were not normally distributed, so we check and we transform them by a square root, and we run Pearson test to check for multicollinearities in between these variables. We did this with the R package MGCB. We first ran univariate GAMs, and then we ran multivariate GAMs with all the variables, and the model selected was the quasi-Poisson because we had count data per area. So the result of this analysis was first the effort map. Here we can see all the effort carried in the bay in this 10-year period, in which we can see that the whale watching season increased in months, so it's a bit longer now, and we also have higher number of trips, and we can also see that the center of the bay is strongly surveyed compared to the offshore area. For the number of sightings of harbor porpoise, after all the filtering, we got 554 sightings, and we also can see here that the number of trips compared to the trips with harbor porpoises are very unequal, so this is the reason why we have such a low number for such a long period of time. We also did a spatial spew map, so we assessed the effort and the number of sightings spatially, and I found this graph quite interesting because even if all the effort was carried in the center of the bay, porpoises sightings were always next to the coast. For the differences between years, we found this with a significant p-value, especially the years 2009 and 2010 compared to the rest. And in between months, we couldn't find any differences. For the sea state values, we can see that harbor porpoise sightings were always almost done under B43, and the GLM gave us a positive outcome out of this. For the kernel density estimations, we first did the annual kernel density in this 10-year period, but it didn't give us much interesting information. As you can see, there's no clear pattern of the distribution of the species, but thankfully the monthly kernel density gave us a quite clear key area in the western part of the bay. There's also some quite of a hotspot in here, like near Husavik town. We can see that there's still also some sightings over there that might be interesting. For the GAM analysis, we first did the multicollinearity matrix in which we saw that actually, if yeah, bathymetry and distance. Bathymetry was explaining latitude and distance to the coast, and we check this, like, if you check this matrix like this, you can see the values that are bigger, and we check this with the Pearson test, if it comes. And we actually saw that depth was significantly explaining latitude and distance to the coast, and so we released this variable from the model. In the univariate GAMs, we basically check the importance of each of these environmental variables, how much these were explaining the distribution of the harbor porpoises individually. And the p-values bigger than 0.1 were considered for exclusion, but none of them were. So we put them all in the final model, in the multivariate GAM, and we were releasing each of these terms by the p-values and the GCB scores, as is standardized for this analysis. And we end up with this final model in which temperature, distance to the coast, latitude, and longitude were significantly explaining the porpoises distribution with a 31% deviance, which is quite a good number compared to other studies that I checked. The final graphs for this analysis were these ones, in which we can see that almost all the sightings of porpoises were done between temperatures between 5 and 10 more or less, if we check the upper one. And we also can see a negative relationship with the distance to the coast, so farther from the distance, less probable to see the whales. The latitude and longitude area selected here gave us a similar area in the bay that the kernel densities, so we have some consistency in between analyses. So finally, discussing these terms, the effort analysis told us that the whale watching season was longer and the center of the bay was strongly surveyed. Maybe porpoises sightings are very low because they are not the most interesting species for these whale watching companies. And even if we found some higher numbers in the month of June, for example, it was due to the weather conditions, not so much because there's some kind of seasonality in the species or something like this, because they are there all year long. They might be also because they have a tendency to avoid vessel noise because the pressure of whale watching is very high in this bay. The spew values might be biased because of the platform again, and it's interesting to comment the monthly spew were not significant even if the effort is strongly done during the summer months. Okay. The sea state was interesting to include as a covariate in the GAM analysis, and the kernel densities show this area that is also being seen that is interesting for other cetacean species in the same bay. The GAM analysis could include more variables relevant for the porpoises, like tide cycle or diel phase, and maybe it has some bias because it's been done always in opportunistic platforms. So I just want to comment some study limitations because we use whale watching boats. Data was collected by volunteers, so there was some bias input that way, and the environmental variables were average. So this might be not so relevant. And I wanted to include a reliable prey distribution, but we couldn't find it. It was quite hard to talk to the fishermen and the companies, and I prefer not to include it in my model. So to conclude, this is the first study in harbor porpoise in this bay, because it's not such an interesting cetacean compared to the rest that are there, and maybe combining visual and acoustic data might be interesting because we know they are very active acoustically. The kernel density estimation gives us this western part of the bay that should have more studies to understand the biological dynamics going on there, because it's been seen very important. And the spew values were not so interesting, but the sea state is definitely an important variable to include in future analysis. And the GAM analysis might give important information for doing conservation and management strategies in the future in this bay. So I just want to thank the North Sailing company, the research center, and especially my supervisor, and my promoter and my colleague that helped me a lot with the RStudio data. And that's it. Tack för er.